All right. Hello, everybody. Can you hear me okay? Yes? Hello? All right. So sorry for the delay. Lots of little problems. My name is Rakan, and why is everybody over there? I thought I took a shower this morning. Anyways, just before we begin, there's something that I keep on getting from a lot of people is, hey, I love this thing you're working on, this stenography project. It's awesome. Just so you know, there's a big difference between steganography and stenography. This is stenography. All right. I'll just go over what information hiding is in general. There are many different kinds of information hiding. I'll go over all the different classes, focus on software marking, and in theory, how things work. Thing is, in practice, a lot of things are very different, so I'll go over everything. Anyways, steganography is what you know. Who knows what steganography is? All right, sizable chunk. The idea is to be able to hide something in such a way that a third-party eavesdropper would not be able to detect that there is a message being passed on. It doesn't necessarily have to be efficient, data rate-wise, or be tamper-proof in any way. As long as the person in the middle can't tell that you're trying to communicate, then it's okay. Covert channels is also a kind of information hiding in the sense that you're sending information, but it doesn't either have to be stealthy or resilient or even tamper-proof. Anonymous communications are also a form of it in the sense that what you're trying to hide is the endpoints of the communication. You could literally post something on a Usenet group and for everybody to see, but as long as nobody knows who posted it and who's reading it, then now a big chunk of information hiding work is done in copyright marking. Two kinds of that, robust and fragile. Most of you probably know about watermarks, which is embedding an identifier into an image, a sound recording, or whatever, in order to be able to later on claim ownership, copyright ownership on the medium. So you see people doing it in images, you see people doing it in MP3s. Those marks need to be robust in the sense that if anybody would come and take the medium and try to tamper with it, they shouldn't be able to remove the mark. Otherwise, you basically lose that ownership. Fingerprinting is a form of copyright marking. It's a little bit more specific than watermarking in the sense that you're not just trying to claim ownership on the medium, but you're trying to uniquely identify the person that you issued this medium to. So if I give Joe Schmo a picture and I've only given it to him, then I put a little identifier in it that says I've given this identifier, this piece of image to Joe. This way, if I ever find it on Kazaa or BitTorrent, I'll know that Joe is the person that released it and he gets in trouble. Fragile marks is a little bit different. What it is you try to make the mark so non-tamper-proof that anybody trying to, say, Photoshop an image or modify the medium in any way, you can immediately prove, say, in court, that this medium is not the original medium and therefore cannot be used as a proof for whatever the court case is about. Historically, information hiding has been used for a long time, back since the Romans. Back then it was generally through obscurity. So what you'd do is you'd have a secret way of encoding your information, and nobody else would know about it except the endpoint. And in that way, it would be really easy for you to just send information. Just say, okay, if I do, I don't know, if I use this letter instead of that letter, then it means meet me at noon, wherever. But since then, a lot of things have changed. People have gotten more educated. A lot more people can read and do research and know about math, and they can reverse engineer the algorithm. So instead, now, what people don't use security soap security anymore. But it's still used, and the reason is that for some things, such as reverse engineering and anonymity, it's very difficult to create a system that's robust and works always 100% of the time. Most of the time, what you're trying to do is just stave off the attacker for long enough that that by the time he breaks your system, it's all right. The system isn't going to be used anymore. So, say for video games, if it takes a week for an attacker to break your system, then you're in trouble because you lose a lot of sales. But if it takes him 6 months, maybe in 6 months you won't be selling them any games anyway. So it's okay if there's a crack out for it. So back to historically, camouflage used to be used a lot. So you would do things such as have little pinholes right next to letters where the human eye can't tell, or invisible ink, tricks like that. Or you could hide the message in a very specific part of the document, but a casual observer wouldn't necessarily know to look at that, say, paragraph, third paragraph, second sentence, to find the data. And what you do is things such as maybe change the spacing in between the lines ever so slightly, or use a different font, or do things like that. But that's very easy to break, because all an attacker needs to do is change as much things as possible throughout the entire document, and odds are he will hit the location where you've hidden your data. So as a result, what people do is spread the hidden information everywhere, which could simply mean have multiple copies of the information everywhere. And if one part of it gets broken, then odds are that the other bits won't be. You can also use spread spectrum encoding techniques and other stuff. So throughout this discussion so far, I've mentioned 3 general things about classes of information hiding techniques. What you're really looking at is how much data can you encode, how stealthy is it, meaning can a third party easily tell that there's something fishy going on, and how resistant is it to tampering. These are the 3 criteria that we use to evaluate any information hiding system. And there's several attacks against information hiding system, and they're also divided into 3 categories. One is subtractive, meaning if you have a medium, which I represent here as that box with watermark and a W, subtractive attack simply means that an attacker is able to gather enough knowledge about where and what the mark is to precisely locate it and literally strip it off. Now, sometimes he's not able to get that much information, so he tries to mess around a little bit with the medium, and maybe, say, if it's an image, crop a whole chunk out of it. Now, that's okay as long as the resulting medium is still usable to the attacker. If it is, then the information hiding system has failed, because we can still use it, or we can still use the medium despite the mark being taken out. So in this illustration, we have our little friend here with his chainsaw attack the mark for us, and then the result is just the medium with nothing in it. Distortive is similar in that maybe the attacker doesn't know exactly where it is and what it takes to take the mark out, but you can try a few things, shoot blindly at the medium and see what happens. Maybe the mark gets distorted, and to such a point that the program that recognizes the watermark isn't able to recognize it anymore. So in an image, You could do little things like maybe scale the image, shear it a little bit, stretch or whatever, or maybe warp little points in it so slightly that the human eye doesn't necessarily notice the difference. The illustration is just our dude here jumping up and down on it. And we end up with W prime, which is a different watermark than what we started out with. An additive is just that we try to override the medium with a new watermark. And hopefully it'll overwrite the first mark. And if it doesn't, then we have two marks that are living at the same time in the same medium. And it might make it difficult for the recognizer to see the mark to begin with, or for somebody to prove that this mark, the original mark, was there before the added mark. You might not be able to tell the difference, which was there before. A lot of different mediums have several information hiding techniques. They're a little bit different in each: sound, image, video, text. A lot of research done. There hasn't been a lot of research done in information hiding in binaries. And the main reason for that is that it's a low redundancy medium. Now, I haven't spoken about redundancy yet. What you need to be able to convey as much information as possible in a medium is to have the medium be redundant. So the English language is a redundant language, meaning there's several different ways you can say the same things. Probably some of you know the Monty Python dead parrot sketch. This guy walks into the shop and he goes, "My parrot's dead." And discussion goes on, and basically we end up with this guy saying, "This parrot is dead, this parrot is no more, it has ceased to be, it has shuffled off its mortal coil and joined the choir invisible, this is an ex-parrot." Many different ways of saying the same thing. So if you agree beforehand that what you want to do is convey information with that sentence, "This parrot is dead," you could say, if I say this parrot is dead, it means meet me at noon over there. If I say this parrot is no more, then meet me at 1, and so on. That's what I mean by redundancy. And binaries, executable files, have been designed to be as non-redundant as possible. So it's really difficult to convey information because there are many different ways to say any given thing, but it's especially hard with binaries. So we'll go over how we do that. And techniques can be divided in two different ways. There's static marks and dynamic marks. Static is the simplest. You have static data marks, where in your code you would have an array with some data in it, such as copyright, Microsoft, blah blah blah, and you could use that as your mark. So all you need to do is do strings on the binary, and you would see the mark right there. You could make it anything you want, but as long as it's data. It could be like a switch statement. It could be whatever you wanted. A code mark is you could do a couple of things. One, play around with the ordering of the way you write your code. So say maybe when you're writing different functions, instead of having function A at the top, function B after it, function C later on, you could reorder them in any way you wanted. And given a large enough number of functions, you could uniquely say, okay, this has to be my code because look at the way those functions are ordered. Yeah, that's one way. The other way is you could have different pieces of code in different executables. So in the executable I give that I release, say, at Black Hat, I would have this chunk of code that doesn't necessarily do anything, but it's just there, and I can grep for it, and I can change that piece of code because it's garbage code anyway. This is another way of doing static code marks. It's where you have a bunch of statements, and you can arbitrarily decide what your control flow is going to be. So it doesn't necessarily have to always go from A to B, from B to D. You can reorder it any way you want. It's just junk code anyway. Now, as it says, it's easy to implement. You just write your code in a certain way and you have your information hiding system. But it's really easy to break, because all a person has to do, an attacker has to do, is to look at your code, see that there's a string copyright Microsoft, and overwrite it, and what are you going to do? Or they could analyze the binary and find pieces of dead code that do nothing or are highly redundant, and just overwrite them with something that either does something or optimize your own code or whatever. So instead, what people do is have dynamic marks. Now this is much more difficult to break, because basically you have to know what the program is doing in order to try to break the information hiding system. And it also relies on input. So you cannot just look at the program and say, oh, this piece of code looks weird. The information hiding code, the mark reacts to your input. So under normal circumstances, it probably does something very legitimate, such as, I don't know, print something to the screen or calculate some number. But given this very specific set of input, it will display the mark or put the mark in a recognizable way for you. So I'll give you examples of that. Easiest is Easter egg. Type about Mozilla and you get this stuff. So what you could do if you were trying to hide a mark in your software is trigger for something like this. And if when you type about Mozilla in some other browser, you get the same thing, then you're like, oh, what's going on? This is something weird. Maybe they stole some code. But that's easy to break. So instead, there's dynamic data structure marks, which you have some variables intermingled in your code, and throughout the normal execution of your program, you do stuff to those variables. Maybe you really use them to do what your program is intended to do, parse a URL, whatever. And given a set of inputs, very specific inputs, at the end, you're left with some values in those inputs. And those values are your mark. So in this case, it's the ASCII text, the Great Mahir. You just keep pounding input at it until it gives you this, and then you know that you found your mark. Even more difficult to break is what we call dynamic graph watermarking. The premise of it is that you choose two large prime numbers, P and Q, and you compute P times Q. It gives you some other large number. Now, if you can embed this number n in your code in such a way that it can't be tampered with, and then later on you're in court and you're saying, okay, I have a proof that this is my code, and the proof is I can factor n. I can show you what the prime factors are. I can show you what P and Q are. If you can do that, then it proves that basically it is your code. And one way to do such an encoding is what we call a radix K encoding. And I'll explain it here. What you have at the bottom of the screen is a linked list of items. And depending how the lists are connected to each other, that's how you encode data. So for example, the first item all the way on the left, that would be, this is radix 5 encoding. You have 4 elements. The first element is, 5 elements. Yeah, the first element is your k to the power of the number of your elements. So here it's 5 to the 4. It points not to null, nor to itself, but to the next item, which means it's 2 times 5 to the 4. The next item is 5 to the 3. It points to null, so it's 0 times 5 to the 3, 5 to the 3rd. And then the other one is 3 times 5 to 2, and so on. And this number is basically 7 times 191, which is 1337. So if you were to encode 1337 into your code, you could prove that it's yours by saying, look, I know how to do 7 times 191. Obviously, what you really want is a really large number because this is trivial to factor. But this is the basic idea. There are many other kinds of encoding schemes. This is just one of them. The reason why it's nice is because it can be very difficult to reverse engineer. There are a lot of tricks you can do with data structures and pointers to confuse an attacker as to what exactly you're trying to do. A pointer is it's just a number, 4 bytes, 32 bits. It can be a number that you actually use in your computations. It can be a pointer. It can be text. It can be anything you want. So you can use that to your advantage and confuse reverse engineers. So that's why it's used. Another thing you can do is dynamic execution trace, meaning that your code typically runs in a certain way. If you were to do hello world, it jumps to, your print statement says hello and then exits. And that's the typical way that it functions. In a browser, it can get really complicated, where it's doing lots of things, going through various many addresses, doing a whole bunch of different system calls and all of that. And you can keep track, say, of the last 2 bytes of the addresses that it runs through while it's executing the program. And you can use that as a mark, because normally this is how it executes. But if you give it this specific set of inputs, this is how you expect it to execute. And if it executes in this way, then you know that you recognize your program. So if somebody steals a chunk of your code, then this is one way you can use to recognize it. Now, there are attacks against every one of these things. Simplest attack is that you take the original code and you just mangle it beyond comprehension. On the left, I'm just assigning 3 variables. On the right, I'm doing the same thing, but it takes you a while to figure out that that's actually what I'm doing. And to make matters worse, as a human being, we can figure it out. But to get a program to go through and realize that these 2 things are the same, it can be quite tough. So these were attacks on static marks. On dynamic marks, a bunch of attacks too. As I was saying, we have this list of pointers of this data structure. You can add a whole bunch of indirection if you wanted to. Say, instead of having this data structure point to the next one, there's no reason why it couldn't point to a 3rd one and then which points back to the original one, as long as you change your code appropriately to take into account these things, then you're fine. Or you can reorder the data, or there's many things you can do to frustrate the dynamic marks. Now in practice, I've been talking a lot about how you would look into the code, see what it does, and modify it to make it do what you want it to do. But that's true if you have the source code. If you don't have the source code, then what are you going to do? So in practice, all of these theoretical marking systems, especially dynamic marking systems, only really work when you have the source code, or if you're dealing with Java or .NET, where basically it's trivial to reverse engineer the executable code. And the reason for that is that the reason that it's difficult to reverse engineer things other than Java and .NET is that the programs get compiled down to machine code, in which case it's very difficult to tell apart data and code. Meaning, is this a number or is this an instruction that does an addition? They're all the same length, they all look alike, but depending on the context, one is code and one is data. And for a disassembler, it's impossible sometimes to know for sure this is what's going on. The disassembler will give you a an estimate, like this is what it thinks the code is doing, but by no means is that correct, necessarily correct. So we can't use these advanced techniques of dynamic markings because we need the source code, and unless we have it, it's difficult to do stuff such as insert a data structure in the middle of the code that does all this random stuff that we use to detect a mark. The only way to do it is for you to write the marking system into your code before you've even compiled it. And sometimes you can't necessarily do that, especially if you're trying to hide data in code after. I'll show you what I mean. So little work has been done on machine code watermarking. The only work that's been done has been on if you have the source code. And all right, so viruses. What hides information in machine code? Virus. Typically, a program runs, it starts somewhere, and it just keeps running, follow the green arrow, and eventually it ends. What viruses do is that they add some code to the end of the executable, and hijack the entry points so that they can run their own code. And when they're done running their own code, they go back to where they started and just keep going. Now, the problem is that it's very easy to detect sometimes. I mean, often, if you just have a piece of code right there at the end of your binary, and you see this jump, and then it comes back, you're like, wait, why is it doing this? It looks a bit bizarre. And antiviruses have long flagged this kind of behavior, and nobody writes viruses this way anymore. So instead, what people started to do to avoid antivirus detection is that they would encrypt the body of their virus, so that every instance of the virus would look different. I skipped something. Before looking at this behavior, a lot of antiviruses would do is simply grep for the virus. If you knew that this worm is written in this given way, then all you need to do is grep for this particular sequence of instructions that you can only find in this worm. And if you find it, you found your virus. So what people started doing is encrypting the actual body of the virus, so that every instance of the virus would look different. And as it ran itself, it would decrypt itself and then run the decrypted code. So it would have this fixed decryption routine at the beginning of the virus code. So antiviruses started triggering on that instead. They're like, aha, we'll just use that, and that decryption routine stays the same, so we'll just trigger on that instead. So that's encrypted viruses. So as a result, we got polymorphic viruses, which instead do not have a single fixed decryption routine. They also change their decryption routine. There's a lot of different ways that decryption routines can be changed, and I'll talk about this a little bit later. Now, metamorphic viruses are but the thing with the polymorphic viruses is that at some point, they have to decrypt their code and run it. So at some point in memory, you'll have the sequence of code that's the virus. So instead, what the antivirus needs to do now in order to detect the virus is just to wait for it to decrypt, and then it flags the instance in memory, and you're done. So now what people do is write metamorphic viruses, which don't even have a decryption routine, and the way it works is that it simply randomizes code every time it infects a new binary, and that's what we're going to use to hide information into binaries. So what I mean by randomizes code is that it does a lot of tricks. So it does things such as register swapping. There's no, in assembly code, there is no reason why you would choose to store something into, say, register A instead of register B or register C. You could pick and choose. It's really up to the programmer. So what a metamorphic virus can do is just that at every instance, it knows these are the registers I'm using. These are the registers that have already been used and that I'm not allowed to touch, say before, used by code that's before our code. And you can swap them around. So the first time you used a register A, EAX, then you use EBX, and then the second time that you infect someone, you use EBX first and then EAX. So anybody trying to simply grep for the virus code, be it in memory or elsewhere, the new code looks different. I don't know if you can see the red too well. On the left-hand side is the actual binary representation of the virus code, and almost half of the code is changed now just by virtue of register swapping. There are many tricks. This register swapping is the simplest one. Instruction substitution is another one, in the sense that there are many different ways to do the same thing, and I'll go over this in great detail later on. But you can, in the same way that you do an addition, you can do subtraction, but negate the operand. You can have various data values in your code and just that you don't actually use, and just randomize them every time that you infect a new host. You're not using them anyway, and from the antivirus point of view, all it knows is it's trying to grep for this fixed string, and this fixed string is not there anymore. NOP and garbage insertions, so there's no reason why your code has to stay the same size. You can just add garbage instructions in the middle of your code, and it doesn't change your functioning. Branch reversal, I'll go over all of this a little bit later on. So Hydan is this tool that I wrote that uses some of these techniques to hide information into binaries. And it's generic in the sense that it takes whatever input you want and just tries to hide it as best it can into the binary. And currently it only works with instruction substitution, meaning it looks at the binary, finds instructions that it knows it has equivalence for, and then substitutes those instructions around. And depending what the substitution is, it means something or it doesn't. So I'm gonna try the demo, but I don't know if we have network. All right, this laptop is dead. No. It's turning on. I don't know, it turned off. Yeah. Can I just unplug it here? Yeah. A little flaky. All right, we'll try. If it works, great. How do I get the screen to come up? This guy? All right, great. Oh, I can't see now. Or you know what? Let me. Yeah, let me.
Set it up.
Yeah, set it up.
Yeah, it's
Right.
function, I think.
Okay, it's being really slow. Demo gods aren't happy today. Somebody like to tell a little joke while we wait? Okay, never mind. It's okay. It's just being really slow.
Function 07?
No, it's just being too slow for, yeah. Okay, well, I'll just describe it. Basically, take a program, take Hydan, my program, and you feed it a binary such as bin ls or whatever you want, and you feed it also a message. So it could be anything, hello world, hi, how's it going, anything you want, and it just hides it into the program. I wish I could show it to you. I have a really nice picture that I would have stored in there, but. In any event, what ends up happening is that you have a new copy of binls now, runs identically to the same, to the original, and it has the exact same size. Nothing's changed as far as functionality or size, and but if you try to extract the message using Hydan again, which prompts you for a password, by the way, you get the original message back out. You can download this, by the way, from my website. I don't know if I put a link in here, crazyboy.com/Hydan. That's an old copy. A new copy will be up soon. Now, the way it works is that you have different instructions that mean the same thing, and I use them to substitute. One way is addition. Add EAX 50 or whatever is the same as sub EAX negative 50. Standard arithmetic. So if I can decide from the onset that addition means bit 0 and subtraction means bit 1. And so when I encode something with Hydan, I just go into the binary, disassembling it from the beginning, just keep going, keep going. Every time I see an addition, I check to see, or a subtraction, I check to see what it is that I'm trying to embed. Is it a 0 or 1? And I flip accordingly. Addition and subtraction is just one way, and since there are only two ways, you can only embed one bit of information into it. There are other instructions. One of them is a test instruction, which simply compares two registers and tells you if they're equal, if one of them is greater than the other, and whatnot. You can do this in different ways. If you're only looking at the same register, so EAX, then you can do test EAX, or you can OR them together, or you can actually AND them together. Now you see there's two different OR instructions in there, and I'll explain this a little bit later, but there is more than one way to have the same instruction depending on the ordering of the operands. I'll talk about it a little bit later. So in any event, here with the test instruction, whenever we see a test instructions, we can substitute it in 4 different ways, meaning we can encode 2 different bits of information for each test instruction. And test EX is something that we see everywhere in machine code. So an example, this is code that I found in BinLS, I think. And it's just to show you that just in this piece of code, I can embed 4 bits of information. The first bit is with add. If I wanted to embed 0, 1, 0, 0, add is already 0, which is what we spoke about before. So I keep it the same way. Then I find AND EAX, which is one of the ways that I just mentioned for test. 2 bits right there. And then there's a sub a little bit later on. And what I want is a 0, which is an add. So I just flip it around to what I want it to be. Now, this is fine and dandy, but if it's just done this way, then it would be pretty easy to detect that you're trying to hide something in a binary if an attacker were to execute the binary. So, and the reason is that ASCII, assuming that you're embedding ASCII, is repetitive. Every first most significant bit is set to, I think, 0 or 1, one of them, and it's always that way for standard ASCII. So if you were to analyze the code, the binary code, you would see every 8-bit repeating bit 1, bit 1, bit 1. Like, okay, something is definitely hidden in here. So instead, we encrypt it, which simply whitens the message, makes it look like random noise. It could be anything. You can never be sure if it's ASCII or something else. And there's a problem with encryption is that you want to be able to know how much to extract from the binary. Because say in BinLS you could embed, I don't know, 3K of message into it, but you don't necessarily have 3K to embed into 3K as a message. Instead, maybe you just have hello world, which is very short. So you have to specifically encode the length into your message. But then if you encode the length, then that's an easy way for an attacker to detect your message, because all he has to do is say, okay, the length is a 32-bit or 64-bit wide field, and this code can only contain a maximum of, say, 3K of data tops. So odds, like, the number can definitely not be greater than 3K for the length of your message. And then you can look at that field. Does it look like it's actually less than 3K? Yeah, it does. Or it has a whole bunch of zeros in front of it because the length is really small. Then you're like, it's a pretty good indication that you have something hidden in there. So instead, what we do is take the password. I would have showed this to you in the demo, but Hydan prompts you for a password, makes a SHA hash of it, and then XORs that with the length. So it looks like garbage, but when it comes time for you to retrieve that data, it's trivial for Hydan to find it. And another thing we do is that if, by the way, all of these techniques are to make an attacker's life more difficult. because we're trying to do steganography, and we don't want an attacker to easily be able to tell that that there is something hidden in the program. So random walk is one thing that we do as well, which is that if you were to do what I talked about before and simply go through the program line by line, and as soon as you see an addition or a test or any other instruction that we have equivalents for, and substitute that, then what you'd end up having is the program itself, and at the top you'll see all these substitutions, this weirdness in terms of what instructions are used, and then afterward all you'd see is the regular test and adds and subs in the given frequency that they usually occur in. So what we want to do is try to embed the text evenly all over the medium, and that's what we call a random walk. So these squares are just code blocks that we can or cannot embed into. The blue ones are the ones that we can actually embed into. And what we do is that we pick a random number. Say the first number we pick is 2. So we go and we embed data into the second block. And then we pick another random number. It gives us whatever, 4. We end up at that block. And we just keep going, keep picking random numbers, next one, next one, next one, and so on. And eventually, we cover all the blocks that we wanted to cover. And the way we're able to know what the random number is going to be at decoding time is that we seed the random number generator with a hash of a password. So the end result is that when you call the random number generator, we know for sure that this is the sequence that it's going to have. The trick is to know how to seed it to begin with. So an attacker doesn't know the password. He wouldn't know how to seed the random number generator, and therefore wouldn't know how to perform the random walk and in what order to decode the code blocks. Now there are some problems in that when I said equivalent instructions, they're not always equivalent. There are some edge case scenarios, such as add and sub. In this example here, I'm clearing a register, so EX is 0, and then I'm adding -1 to EAX. In this case, the result is that EX is -1, the overflow flag is 0, and the carry flag is 0, which makes sense. Now, what happens if I subtract 1 from 0? It should give me the same result, right? It doesn't, unfortunately. The carry flag gets set. So there are little tricks like that, the little problems that make it that some instructions are really not equivalent. If I were to simply not use them because they're not equivalent 100% of the time, then there would almost be no way of encoding any data at all with instruction substitution. There are always some edge cases like this. So what you do is simply you scan forward. You have to disassemble. You know where you are in the code, and you scan forwards for any instruction in the execution flow that may overwrite the flags that get modified. So in this case, if I scan forward and I see that 2 or 3 instructions later, there is some other addition or a multiplication or something that sets the carry flag, and in between those instructions, there is no instruction that actually checks for the carry flag, then I can do whatever I want to the carry flag. It never gets checked anyway. It gets clobbered. Right. There's another problem in that I showed you the example when we have 2 instructions or 4 instructions that we can embed into. What happens if you have 7 instructions? If you wanted to embed 3 bits of information, you would need 8 instructions, but with 7 you just can't do it. But it's a shame because otherwise you'd have to resort to only using 4 of the instructions and only embed 2 bits of information. So you're wasting a few instructions. So what we do quickly is just use one of the instructions as a joker, where you say, if this instruction is present, then we're not embedding any information. And all the other ones are used to embed 3 bits of information. So in the case of 7 instructions, I use 6 of the instructions to embed 3 bits of information. And then if there's any instruction that any data that I would otherwise try to embed that needs the other 2 instructions, then I just embed the joker and say, sorry, can't use this. So as a result, for 7 instructions, instead of having to only be able to embed 2 bits of information, I can actually embed 2.58, which is log 2 of 6. Oh, and the reason why that works well is because we assume that the data is random because it's encrypted. So we have an equal distribution of values. So we won't get a case where we have, say, data that's exactly what we cannot embed. So what are the issues here? Issues that it's detectable. Despite what I said about additions and subtractions being equivalent and all of that, they're not actually created equal in the eye of the compiler. Compilers choose oftentimes to use adds exclusively or subs exclusively in some places. And for example, they often do not ever use a negative subtraction. So sub EAX -5 is very, very, very rare. So if you were to analyze the code and you see a huge number of negative subtractions, then you know that there's something very fishy going on. It's a relatively low bandwidth as far as steganographic tools goes. Outguess, which hides in JPEGs, can embed 1 bit of information for every 17 bits of cover text. And Hydan can only embed 1 in 110. It's still a lot if you look at things like Microsoft Word, but if you look at BinLS, it's not really that much. You can still hide more than a message. It's not the issue. It's just it's an order of magnitude different with other tools. It's also easy to tamper with because we're using static code marks, basically. All an attacker needs to do is to know ahead of time that these are the instructions that we can embed into, which are addition, subtraction, test, and a whole slew of other ones. If they know that, then they can just go around flipping around randomly all our additions and subtractions, not knowing necessarily if we've actually hidden anything in them, but it would effectively destroy our text. And it also breaks self-modifying code, which I don't see as too big of a problem because I don't know if there's that much self-modifying code out there other than viruses and stuff like that. But if you were to rely on the fact that this addition is an addition and it has to be an addition, then if you embed with Hydan, you would break that and might possibly break your code. I'll do a QA session just afterwards. Yeah, some statistics anyways. So future work. Now, I told you what the problems were with Hydan and how it can be broken. There's one way to get around that is to use reordering. And what I mean by that is that if you have a bunch of different code blocks and you want to be able, you can reorder them because, say, functionality doesn't depend on the ordering of the blocks. That, as I spoke about earlier on, if you have function A, function B, function C, and so on, it doesn't matter where in the code they're located. As long as you call the right address and you pass the right arguments, it'll return back to where you expect it to. So you can take those functions and just put them anywhere you want. And depending on the order that on the order of those functions, you can embed data. Now, given n things you can reorder, there's n factorial ways to reorder them. And basically, there's log 2 of n factorial bits, which can be quite a bit. If you have only 2 things, it's 1 bit. If you have 64, it's 295 bits. So it grows not exponentially, but pretty quickly, more than linearly. The top one is how fast it grows in terms of how many bits you can embed. It's roughly n log n. I'm gonna rush through this because I'm gonna have a little QA session, but yeah, basically this is just a way to embed data with reordering. If you have ABC, ABC is 0, ACB is 1, and then there's an encoding algorithm which basically means that the way it works is that you take the number of bits of your input and you end up with a number. Say, in this case, we can embed 4 bits because we have 4 items, and that number is 13. You decompose it along the factorials. So 13 is 2 times 3 factorials plus 0 times 2 factorials plus 1 factorial. And then that 2 and 0 and 1 determine the position of the item you're looking at with respect to the list in front of it. So if you have a string ABCD you want to reorder, the first item is the second item in the list, meaning the third in base 0. So it's C. Then you move on to the next one. It's you're left with ABD. You want A to be the 0th item, correct. You move to the next one. You want B to be the first item, so you flip it with the first item. That's one way. It's provably optimal and worked good. Decoding is simple, the same thing. Lots of things can be reordered. Functions, as I said before, independent instructions, and that if you're doing you're adding something to a register and then you're adding something else to a different register, there's no reason why you need to have them in that order. You can flip them around any way you want. And oftentimes you can have a quite long listing of completely independent instructions. Arguments, the way you call functions, you can change these things as long as you change the function itself, the order in which it pops arguments off the stack. Register allocation, data, you can swap those things around. Say if you have a string in your code, it's in a given point in the code, it's an address. If you move that string elsewhere, then as long as you just change the address to point to the correct place, you're fine. And lots of stuff. This is an example of instruction reordering where you have the top 3 instructions are independent, and you can flip them around any way you wanted to. So move $2 into EAX, 3 into EBX, and push ECX, completely independent. You cannot reorder the call because when you're calling a function, you're assuming that the registers have the value that you thought they would have, so that you can't touch, but all the others you can. A problem is that what happens if I reorder those 3 instructions, but somewhere else later on in the code, you have a call that comes back to in the middle of one of the instructions that you've reordered. Big problem. The code doesn't behave the way you expect it to. So it gets really hairy. You have to have a virtual machine to emulate what's really going on, trace all the execution flows to see where the calls end up, and if it ends up somewhere where you could otherwise reorder instructions, you can't reorder them anymore. But it's really complicated and not foolproof. Started trying to implement that into Hydan, but it's being much more difficult than expected. How can this be used? Information hiding, traditional stuff, either copyright marking or simply sending a message to somebody else, all of those traditional things. But in addition, you can use it for security in the sense that you can use it to your advantage for anti-reverse engineering, or you could a lot of the ways some of, say, Windows exploits work is that as soon as the buffer is overflowed, they rely on jumping on a known in a known address in the executable, which happens to have an instruction that we want, say, call EBP, and then it would use that to execute the exploit code. Now, what happens if call EBP isn't there anymore because we reordered things? We took a function that had that call EBP and shifted it completely elsewhere. The exploit will fail. So it could be used in that way. Polymorphism, virus, it could be used as a metamorphic engine, basically. And that's it. I'm running out of time. I have 5 minutes left for questions. Sorry for all the problems with the demo. Wait. All right, it's okay. Just tell me.
Would you consider using maybe like a sorted alphabet instead of just encrypting your text to get higher entropy bits?
What do you mean by a sorted alphabet?
Well, sort of like a block sorting compression. You just take your alphabet sorted, have a link from that the index in the tree where you want to have your character, and maybe use that instead of the encryption, just to increase your damage.
Oh, that's kind of what I do, though. With the reordering? Yeah. Anyone?